Swayam Prabha. Digital India. Educated India.
So good afternoon, students. Yeah. So I am going to discuss with you about quantum chemistry, right? I am sure you are all in the second year or first year of MSc. Yeah. So you must have had some aspects of quantum mechanics, definitely. All right. I am sure. What are the topics that are covered in quantum chemistry in your syllabus? Postulates of quantum mechanics is covered in the syllabus. Yeah, postulates followed by Schrodinger equation, and they would have discussed a particle in a box, harmonic oscillator, hydrogen atom, discussed or not? Yes, sir. Right. So hydrogen atom. So these are the topics covered in the quantum mechanics. How many of you are familiar with operators? You heard about the word operators? Definitely, because you should have, since you have studied all these important topic, which are the classical topic covered in the classical, in the sense classical, in the conventional sense, that these are all covered in the first year MSc. I am sure you are all familiar with the word operator. So I am going to discuss with you about operators, right? And how many of you are familiar with the commutators? You heard about commutators? Definitely. Excellent. So we'll start with operators, spend some time on commutators, right? From commutator we'll work uh, with the harmonic oscillator one more time, alright. So harmonic oscillator you must have solved using differential equation, alright. How many of you are familiar with the technique called power series method? Have you used that for solving harmonic oscillator? No, it's not a problem. We'll discuss slowly. Alright. So you can stop. I'm not going to show any PPT. I'm going to work out things on the board. Alright. So I will do like that. You can stop me any particular point of time. So let me slowly introduce the term operator. Alright. I am sure you are all familiar with what is operator. Alright. Let me go back to our +1 +2, where you have studied differential calculus and integral calculus. Alright. Generally operator is a rule. Alright. So let D is some operator. Let D, you put this symbol on the operator, alright. It is called circumflex, alright. It is an operator symbol. We are also familiar that this kind of symbol is used in our vector, alright. Vector algebra we use this, right. This is the operator. This operator is an operator. Let f of x is a function. I am not rigorously defining function, analyticity and so on, but I am defining f is a function. Now, when this operator acts on this function, I get a new value, I get a new function. What is the function? That I call it as some g of x. This I call it as a new function. So when f of x acts on this operator, I get a new function. Example that I can give here is, I call this d operator as d by dx operator. Differential operator. We are familiar with the differential operator. And then I define function as x square plus 2. function is x square plus 2. This d of f of x, so f of x is going to act on, right, or I am sorry, the d is going to act on f of x, alright. Therefore, this will be d by dx of x square plus 2, right. So, what you will get? 2x, right. So, 2x. So, d f of x, I get a 2x, it is a new function. So, this is the concept of operator, right. So, operator generally is a rule when the function acts on this or the d acts on f of x, I get a new function, alright. Remember this is the way in which it goes. For example, let me take another operator d, right. This is a d square by dx square. This is the second order derivative, alright. So, I will take function as a new function which is x cube plus 2x square plus 4x plus some, let us say 5, alright. So, what will happen here? This d f of x equal to d square by dx square x cube plus 2x square plus 4x plus 5. So, this how many times it will operate? 2 times operate, alright. This is d by dx, d by dx, x cube 2x square plus 4x plus 5, alright. So, this will become d by dx of 3x square plus 4x plus 4, differential of a constant is 0. Therefore, when you operate on this, this becomes 6x plus 4. Therefore, you get a new function here. 2 times if you differentiate, you get a new function g of x. So, this is the concept of the operator. This operator is a differential operator. Most of the time in quantum mechanics, right, the kind of knowledge that we have, right, tells you that these operators are in quantum mechanics are differential operator. I will introduce one more here, right. This is a multiplication operator. Can I remove this? You have written, right. For example, 3 times of x square plus 4x. What is the meaning of this 3 operator? The 3 operator is nothing but this is going to operate 3 times, therefore 3x square, here it is going to operate 3 times, so 12x. So, this can be viewed like this. So, this is the operator. So, this is a multiplication operator, right. This tells you that the 3 to the circumflex tells you that this x square is multiplied by 3, right. Generally, we won't put this operator, but this can be viewed as a operator. Unit operator. What is a unit operator? The unit operator is this x is multiplied by this unit operator, you get x, and you have a null operator. Null operator, null means you are familiar, 0, 0 operator, right. I have a function x is 0 is multiplied by x, so the 0 operator is multiplied, therefore I get a 0. Conventionally, generally we won't use this 1 with operator symbol and 0 also with we won't use that notation, but generally if it is if simply you write x means it is operated by a unit operator. Suppose you have a 0, then it is a null operator. Keep this in mind, right? In quantum mechanics, all right, quite often we come across with operators which represents the position of a particle so we come across with operator which is the position of the particle and momentum of the particle. Generally we come across with the position. Generally the position is represented with a notation x vector or r vector. In textbooks they use bold letter. Whenever you see in the textbook, if you have a x bold letter, it represents a vector. All right. So the position I'm not position of a particle is this. Momentum of the particle is a vector p. It is nothing but p into v. M is mass, v is velocity. All right. M is mass and v is velocity. Right. This is the momentum. So these are very, very important quantities for our quantum mechanics. Position of a particle and momentum of a particle. All right. Very, very important. Keep this in mind. We are going to spend some time on these operators. All right. One is a position operator, another is a momentum operator. All right. So before that, let's spend some time on this. So we have seen in the examples that d by dx of x square plus 4x plus 4. Therefore, the sum, right, is also possible, right? The sum, the function is a sum of some quantities. So I can do the differentiation here, right? I can write the function. Similarly, I can also have a product d by dx of 4x square. That's what you have seen this. A product. So this is a constant. So when you apply the differentiation here, you will take constant out and then you differentiate only x square. Therefore, it is 4 into 2x. Therefore, you write it as 8x. All right. So this is the it can be a sum. This can be a product. I have already shown that. All right. Therefore, product the functions can have all possible combinations. It can be a sum or it can be a difference. Even suppose I can have in differentiation, I am sure you must have done this, x square minus 4x, right? The difference now, this becomes 2x minus 4. Therefore, the function will have summation, can have a multiplication, can be a subtraction. Therefore, all possible, these are all we have studied in our basic calculus, all right. So, this idea, keep this in mind, right. Let me generally define a operator. Let A and B are two operators. I am not telling what is the operator here. Let A and B are two operators. Now I can have, so like in the functions we had multiplication, we had a summation, we had subtraction. In functions that is possible. Similarly, can we have product of A into B? Can we have a product of A into B? Can we have a product of B into A? Right? How many of you are familiar with the matrix? Right? I am sure matrix you all remember, right? So let me spend a few minutes on matrix. Any questions? So I will give you a simple matrix 1, 2, 3 or even this. I am not putting this here. B is equal to 2, 1, 3, 4. All right. I am giving an exercise now. Calculate A into B and B into A. Quick. Again, this is your +1 or +2 pasted. So I have given two matrix. A is equal to 1, 2, 4, 3. B is equal to 2, 1 and 3, 4. I want you to calculate A into B and B into A. Finished? What is the answer? Or one sec. So she says that AB equal to 1, right, 8, 9, 17, 16. 8, 7, 19, 18. So now what is the inference from this? Correct? I have not worked out the product. You have to tell me. BA instead of 8, 6. 6, 7, 19, 18. Right. So you have AB is equal to 8, 9, 17, 16. So what do you observe from this? So AB is not equal to BA. Alright. It is therefore AB minus BA, the difference. So what is the value? So there is, it's not equal, therefore it is not 0. Right. So this is called AB minus BA. This has a value, right? Right. So this is called commutator. So commutator is this. When, so actually we can discuss this from various aspects. I can simply start with the operator and then tell you what the multiplication of the operator and say that AB is not equal to BA. I can start with the matrix and show I can develop the commutator. So we can do this, but it is easy for you to understand because we are familiar with the matrix and then matrix products, product of two matrices we are familiar. Therefore, from this we can develop the commutator algebra. So what it tells you that AB is not equal to BA, alright. Therefore, AB minus BA is called commutator value. This is the commutator value. Since it is put in a bracket, therefore it is called commutator bracket. So this is called commutator bracket. Any question? Any question? Is it clear? What is commutator is clear. AB is not equal to BA. If these two are equal, alright, AB equal to BA, then AB minus BA equal to 0. Right? Generally, the matrix product AB is not equal to BA. In fact, in quantum mechanics, the operator, the product of operator, right? This A operator, B operator, this is called commutator bracket. Since you put a bracket, this is called commutator bracket. This commutator is very important in quantum mechanics. We'll slowly develop the ideas here, right? It's very important for quantum mechanics. And these operators, A operator or B operator, in quantum mechanics, operators are represented in terms of matrices. Operators are represented in terms of matrices. Is represented in terms of matrix. So, definition. So, operator transforms a function into another function. That is a definition. It is a rule. It is a rule. Operator is a rule which transforms a function into another function. So, suppose I have A is an operator, f of x is a function, I get a new function. And A can be a d by dx or simple multiplication operator. For example, I gave multiplication by 3. Alright, it can be a d by dx or it can be a multiplication. Right. So, this is the definition of an operator. Now, you are familiar, nothing great about the operator here. The idea is, it is in quantum mechanics, most of the time what we have is the differential operator. Integration is also an operator, right? The reverse process. We are all familiar with the integration. Y is equal to f of x, and when you say f of x is equal to x to the power n, dy by dx is n into x to the power n minus 1. Same thing, the opposite of this operation is integration. Integral x to the power n dx is x to the power n plus 1 divided by n plus 1. Therefore, the reverse is also an operator. It can be viewed as an operator. Therefore, the definition here is this. But I said that it is important for us to develop the ideas in quantum mechanics with the help of these operators. Right? What is the operator that we are familiar? I introduced that position. Position is an operator. and momentum is an operator. P is an operator. Position, this I said that it can be represented as R vector, this momentum is a vector, right, all these are vector quantities. And we know that R vector is represented as xi plus yj plus zk, right, in 3 dimension. In 3 dimension, you know that this axis is x axis, this is your y axis, this is your z axis. Let us say P is any point, right. This can be represented as x, y, z, and I is the unit vector in this direction, j is the unit vector in y direction, k is the unit vector in the z direction. Therefore, this can be represented. So, therefore, position of a particle is represented with respect to the coordinates at that particular time, right. If it is moving, then P is that point. Another point, that momentum. Momentum is P vector equal to mass into velocity vector, and the particle will have a velocity in x direction, y direction, z direction. Therefore, this can be V I, V y I j plus V z k. Therefore, this is nothing but m into V x in I direction, that is x direction, m into V y into j in y direction, m into V z into k direction, right. This can be written as m into Vx is written as momentum in x direction, I, momentum in this direction, momentum in this direction. Clear? Therefore, Px is the momentum in the x direction, Py is the momentum in the y direction, Pz is the momentum in the z direction. Alright. Therefore, what are the pairs that we have? We have the pairs x comma Px, x direction we have a momentum, and y direction we have a Py, and z direction we have a Pz. Alright. Keep this in mind, very, very important. And we have seen in the past slides of quantum mechanics. Let me state one more time past slides of quantum mechanics. First postulate number 1. So, tell me what is this postulate number 1 in quantum mechanics? Excellent. The physical state of the system is described by the wave function. Right. Physical state of the system is described by wave function psi xt. X is the position, t is the time, right. This is called this psi xt is called wave function, is also called state vector, right. Are you familiar with these terms? State vector, and some people uses this notation. I don't know how many of you are familiar with this notation. What is this? It is called kit, right. this is called the Dirac notation. Writing like this is called Dirac notation. In fact, simply we write like this. We won't write x comma t. In fact, this psi in the bracket, right? The corresponding, I don't know how to now say that, corresponding complex conjugate is written like this. Corresponding complex conjugate. Both these put together is called bracket notation. In most of the advanced quantum books, right, it is represented like this. Try to learn this notation. Any question? See, you have, suppose I have a vector. Let me explain one more time. I have psi of x. This is the state of the system. What is the corresponding complex conjugate? Corresponding complex conjugate, yes, psi star, right? So this in Dirac notation, this is this. Corresponding complex conjugate is this. They form what is called dual space. We'll discuss. If time permits, we'll discuss. But try to understand. These are all introduced in advanced texts. Now, those who are doing MSc in IIT system, all right, they won't use this our regular psi xt notation. All right, they start with only this kind of bracket notation. Even in exams, if you go to CSA or UGC exam, or most of the time you will see bracket notation is used. So try to cultivate the subject along with the bracket notation. The postulate number 2. Our postulate, let psi 1 and psi 2 are two wave functions representing the system, right? Then the state of the system is described by C1 psi 1 plus C2 psi 2. This is called superposition principle. C1, C2 are constants. This is called superposition. How many of you are familiar with this word? You heard about this? No. So this is another postulates. C1 psi 1 plus C2 psi 2 also represent this state of the same system. All right. This is the superposition principle. In fact, this can be, if you have another vector, let's say psi 3, then psi can be written as C1 psi 1 plus C2 psi 2 plus C3 psi 3 and so on. Right. I can slowly take it to linear vector space from this particular point, or there is nothing You need not worry much about this linear vector space. Alright, you have seen in the 3-dimensional geometry, alright, this is your x axis, y axis, z axis, I vector, j vector, k vector, any position vector p, right. This is O, OP vector is represented in terms of xi plus yj plus zk. Now, imagine, alright. So, how do you imagine a 3-dimension? You look at that particular corner, this is your x axis, this is your y axis, and this is your z axis. Now, at this same point, you think that you have one more axis which is perpendicular to all the 3 axes, alright. Then the vector can be represented in terms of 4 dimensions, alright. Let us say xi plus yj zk, some other xyz, the wk, and then I put k some L vector like that. I, j, k, L, these are unit vectors in the directions. Now, if suppose I have at this origin I have n axes which are perpendicular, I know n unit vectors in the mutually perpendicular directions, right. Then I can write the vector OP vector like this: x1 E1 vector, E1 is in x direction, and x2 into E2 direction, x3 into E3 direction, dot dot. So, En in xn into En. So, all these are unit vector E1, E2, E3, dot dot dot. So, I have this is the imaginary. See, you can visualize 3 dimension. At this corner 0, this is your z axis, this is your x axis, this is your y axis. This is easy to understand. At the same origin, I have n axes which are perpendicular to each other, right. In such a way, any vector in the space can be represented in terms of these components: E1, E2, E3, or J1, J2, J3, or I1, I2, I3. These are all notations, all right. But so many components, n components this will have. Therefore, this constitutes a space called a linear vector space. It constitutes a n dimension. I have to define more to say more about the linear vector space. I am not adding that, but we can add more on that. But basically, you understand this first, then we will talk about the more on this vector space. In vector algebra, any questions? Clear. In vector algebra, you define what is called a dot product. In vector algebra, you define dot product. What is a dot product? I have a vector, I have a b vector, 2 vectors, alright. So, let me write in 3-dimensional space, alright, or 2-dimensional. This is a vector, this is b vector, alright. I am going to take a vector, b vector, dot, alright. So, what is a dot b? A dot b is AB cos theta. I am sure you remember this, alright. So, where theta is the angle between the 2 vectors, where theta is the angle between the 2 vectors A and B. So, this you are familiar, right. If A vector, B vector are perpendicular to each other. If A vector and B vector are perpendicular to each other, what will happen? Then cos 90. Cos 90 is 1, 0. How many are saying 1? How many are saying 1? 0. Excellent. Okay, cos 90 is 0. Therefore, A dot B equal to 0. So, if two vectors are perpendicular to each other, what will happen? A dot B is 0. Therefore, here in 3-dimensional vector algebra, alright, what we have in 3-dimensional vector algebra, when you take this I dot j 0, I dot j is 0, correct? I is the unit vector in this axis, j is the unit vector in this axis, therefore I dot j is 0 and j dot k is also 0 and k dot I is also equal to 0, right. In the same fashion, what about I dot I? I vector with I. So, I am taking product of I with itself. I is 1, I dot I is 1, j dot j is 1, k dot k is 1. Therefore, what is A dot A? A dot A. A dot B, use the definition. A into cos theta. Cos angle A with angle A angle subtended by A, it's 0. Therefore, cos 0. Therefore, it is A square. Therefore, A dot A is A square. A square, alright. What is A square? This is 0, 0 and this is XYZ, correct? Xi, Yj, Zk. This is 0i, 0j, 0k. Distance between 2-point formula, right? Use that. Distance between 2 points. What is A square? I am going to calculate that distance, alright. Keep this. I am going to calculate the distance between these. OP square equal to x minus 0 square, y minus 0 square plus z minus 0 square. Therefore, it is x square plus y square plus z square. So, what is this? This I called it as A. Therefore, the distance between this is OP is A. Therefore, my A is root of x square plus y square plus z square, right, or OP square is your A square. Therefore, this gives me the modulus square, right. My scalar product gives me the modulus square here with itself, right. Therefore, this is the modulus square, right. Therefore, the third idea here, the psi square, modulus of psi square gives the probability. Gives the probability. Actually, I have to integrate, I am not showing that. I am sure you have studied that. This integral psi star psi d tau. Tau is the volume or dr is the volume, gives the probability of finding the particle in the space, right. So, you have to understand the correlation between the 3-dimensional space to the n-dimensional space. In 3-dimensional space, the OP square is x square plus y square plus z square, right. This is the length of a particular vector. Here also this gives you something similar to that, alright. This is the modulus of this vector. This is an n-dimensional space, this is in 3-dimensional space. There is a correlation between n-dimensional space to the 3-dimensional space. This is called the linear vector space. There is one more. So, the linear vector space with the defined, the linear vector space is n-dimensional space. In a simple, I'm not adding more algebraic rigorousness here. N-dimensional space with the scalar product, well defined scalar product, right. It's called Hilbert space. It's called Hilbert space. Those who are interested, learn from more physics oriented lectures, right. Lectures even in IIT, NPTEL, you will see lectures by Professor Balakrishnan, lectures by Professor Lakshmi Bala, alright, on quantum mechanics or quantum physics, alright. You can see that in NPTEL, they will very more rigorously define all these concepts, alright. Since we have limited time, I am just giving you some, I am just throwing all these concepts to you. So, this n-dimensional space with a defined scalar product is called the Hilbert space or linear vector space and so on. The fourth important point is linear operator. A term dynamical we have what is called observable. So, any measurable quantity in quantum mechanics is represented by a dynamical operator, alright. It is a dynamical operator or it is represented by a linear operator. What is a linear operator? Let A is an operator, alright. Sometimes you will see in books, they will use a notation A vector with OP, meaning that it is an operator, alright. This A operator, right, generally written as a function of x comma, it is a function of momentum x comma p. In order to elaborate on this, I'm sure in your basic quantum mechanics, you must have studied about operator correspondence. Are you familiar with this term? No. So, operator correspondence. What is operator correspondence here? The position is an operator. It is a simple scalar multiplication operator. Position operator is a scalar multiplication. Momentum is a minus IH del operator, minus IH cross del, and energy is IH cross dou by dou T operator, and P square, that is the momentum square, is minus IH cross del square. I square is, yeah, I square is minus 1 minus, so replace by del square. P square you replace by del square, right? This is IH del, therefore square is del square operator. What is del operator? Are you familiar with the del operator? In vector algebra, you must have seen this, right? Del is I dou by dou x, j dou by dou y plus k dou by dou z. Del square is a dot product. Del dot del, right? That is a del square operator. So what you will get is, it is dou square by dou x square, dou square by dou y square, dou square by dou z square. This is the operator, right? Therefore, these are all the operators that you will get in quantum mechanics.
SwayamPrabha. Digital India. Educated India.